Hello friends, in this video we are going to study about the diagonalization of n cross n matrix. We will study that how a non-diagonal matrix can be converted into a diagonal matrix. So let's study about it. Before starting, first we will know the difference between a diagonal matrix and a non-diagonal matrix. Let's take an example of a 3 cross 3 matrix. This is a 3 cross 3 matrix having 3 rows and 3 columns, and this matrix is called a non-diagonal matrix. Let's take another 3 cross 3 matrix. This is also a 3 cross 3 matrix having 3 rows and 3 columns, but this matrix is a diagonal matrix. So you can see that a matrix which is having all the diagonal elements and all the elements of the matrices are non-zero, then that matrix is called a non-diagonal matrix. That means all the elements, we can suppose that the elements are represented by A, I, J, and the value of I and J varies from 1 to 3. So all the elements, they are not equals to 0, that is non-zero elements. Also the diagonal elements, all the elements are present there. Whereas in the diagonal matrix, only the diagonal elements are present, that is A, I, J. So we have when the value of I and J is equal, that is A11, A22 and A33. Only these 3 elements are present and the rest of the elements are 0, then that matrix is called a diagonal matrix. So this is the difference between a non-diagonal matrix and a diagonal matrix. So in this video we are going to study the method by which we can convert a non-diagonal matrix into a diagonal matrix. So what is the use of this method in control systems? In control systems, we know that in the state space representation of a control system, we have the state model and we have the various types of representations of the state model, and one of the representation is the canonical method. So this method, diagonalization of n cross n matrix, is used to represent the state model in the canonical form. So whenever we want the state model in canonical form, we use this method. We know that the state model, it is given by this is the state model of an nth order multi-input and multi-output system. Okay, so this is the generalized state model. Now in this state model we have the matrices A, B, C and D. These are matrices in this. Now in these matrices, this A matrix, it is a non-diagonal matrix. And if we want to convert this state model, or we want to represent this state model in the canonical form, or we can say the diagonal form, then we have to convert this A matrix, non-diagonal matrix, into a diagonal matrix. So how we can convert? Let's see. Suppose we define a new state vector. A is the state matrix and X is the state vector. So we will define a new state vector. Let x equals to mz. This is a new state vector, and this M is a matrix which is n cross n, non-singular matrix. So we are just replacing this x state vector, that is the original state vector, into a new state vector which is defined by x equals to mz. Okay. Now we are going to substitute this value into the state space equations, that is x dot equals to ax plus bu and y equals to cx plus du. We are going to substitute x by or replace x by mz. So what are the changes in it? The x dot will be replaced by mz dot. Then we have ax. So instead of x we will write mz. So it will become amz plus bu. Then we have y equals to cx. So c is there. Then again mz plus du. So we are replacing the x by mz. Okay. Now if we bring this m to this side of the equation, then the new equation will become z dot equals to m inverse a m z plus m inverse b plus b into u. When this m goes to that side of the equation, that is right hand side, then it will get converted into inverse, the inverse of the matrix. Now we have the output equation as cmz plus du. So earlier our state model was x dot equals to ax plus bu and y equals to cx plus du. Now x dot is being replaced by z dot and we have the new state matrix as m inverse am. Then we have b is replaced by m inverse b. C changes to cm and then d is same as it is. So these are the changes which have taken place because we have replaced the state vector into a new state vector. Okay. Now this matrix M inverse AM, it is now a diagonal matrix. Okay, so what we have done, we have converted a non-diagonal matrix into a diagonal matrix. By multiplying it with the matrix M inverse AM. When we are doing this, then A is converted into a diagonal matrix. Now this matrix M, okay, this M is called the modal matrix. So this M matrix is the modal matrix and this matrix is formed by the eigenvectors and the eigenvalues of the matrix A. So this modal matrix M, it is formed by the eigenvectors as its columns. That is, the columns of this matrix are the eigenvectors, and the eigenvectors, they are determined by the eigenvalues of matrix A. Now so to determine this modal matrix, we have to determine the eigenvectors and then we have to determine the eigenvalues. So how these eigenvalues are determined? Let's take an example. So let's take an example that how the eigenvalues of the matrix A can be calculated and how we can calculate the eigenvectors and then the modal matrix. Let's take an example. So this is the example which we are taking. We have to diagonalize the system whose state model is given to us, and these are the state equations given. X dot equals to 3, 4, 2, 1. This is our A matrix. X plus this is B matrix, and Y equals to Cx plus Du. So this is our C matrix. Okay. So we have to diagonalize the system, that is we have to convert this A matrix, which is a non-diagonal matrix, into a diagonal matrix. So A is given to us in the question 3, 4, 2 and 1. So now first step is to determine the eigenvalues of the matrix A. What are the eigenvalues? Eigenvalues are the roots of the characteristic equation, which is determinant of lambda I minus A. This is, we are calculating the determinant, equals to 0. This is the characteristic equation whose roots are lambda 1, lambda 2 till lambda n. So these are the roots of this characteristic equation, and these roots are called the eigenvalues of matrix A. So what we have to do, we have to determine this characteristic equation, then we will determine the roots of this characteristic equation, and those roots are called the eigenvalues. So let's first determine this characteristic equation. Characteristic equation is given by determinant of lambda I minus A equals to 0. So first we will have this. Because the A matrix, it is a 2 cross 2 matrix given to us in the question. So we will take this I, that is the identity matrix, also as the 2 by 2 matrix. So we have 1, 0, 0, 1 minus A. A is given as 3, 4, 2 and 1. Lambda multiply with the identity matrix minus A. So our matrix will become lambda 0. Lambda should be multiplied inside. So this is what we get. Then 3, 4, 2, 1. So this matrix will become lambda minus 3, 0 minus 4, minus 4, 0 minus 2, minus 2, lambda minus 1, lambda minus 1. This is our matrix lambda I minus A. Now we have to calculate the determinant, and then we have to equate that determinant to 0. So determinant of lambda I minus A we have to equate it to 0. So let's calculate this determinant. Determinant is calculated by multiplying the opposite elements, like lambda minus 3 multiplied with lambda minus 1, then minus of multiplied minus 2 with minus 4. Okay, so lambda minus 3 multiplied with lambda minus 1 minus 4 into minus 2. So it will be lambda minus 3, lambda minus 1, minus 4 minus 2, it is 8, and then minus sign, so it is minus 8. And we have to equate this determinant to 0, so we are going to equate lambda minus 3, lambda minus 1, minus 8 to 0. Now solve this equation. We have lambda square minus lambda minus 3 lambda, so it is minus 4 lambda, minus minus plus, so it is plus 3 minus 8, so minus 5 equals to 0. Now this is the characteristic equation. Now we have to find the roots of this equation. This is a quadratic equation. We can easily find its roots. So its roots are lambda plus 1, lambda minus 5 equals to 0. So its roots comes out to be minus 1 and 5. So roots of characteristic equation are the eigen values of matrix A. So first thing we have calculated the eigen values. Now we are going to calculate the eigen vectors. So for each eigen value we have a corresponding eigen vector for it. So first eigen value is minus 1 and second eigen value is 5. So for first eigen value we have the eigen vector C1 whose elements are C11 and C21. For second eigen value we have the second eigen vector whose elements are C12 and C22. So we have to find out these two eigen vectors. How we are going to calculate it? These eigen vectors can be calculated by solving this equation lambda 1 I minus A into C1 equals to 0. When we are going to solve this equation, we will get the eigen vector C1. So just substitute the values. Lambda 1 is minus 1. Then we have I. I is the identity matrix. So 1, 0, 0, 1. Then minus A. A is 3, 4, 2, 1. And this whole has to be multiplied with the C1 matrix, which is C11 and C22. 1. C2 1, and it is to be equated to 0. Now let's solve this. We have minus 1 here. So minus 1, 0, 0, minus 1, minus 3, 4, 2, 1. Minus 1, minus 3, minus 4, 0, minus 4, minus 4, 0, minus 2, minus 2, minus 1 is minus 2 again. Then we have this C11, C21 equals to 0. Now we are going to multiply these two matrices. So we are going to get two equations, and those two equations will give us the value of the two variables C11 and C21. So let's solve these two equations. We have So when we will solve these two equations, we will get the value of C11 and C21 as 1 and minus 1. So we have got our first eigen vector. Now for second eigen vector, we will take the second eigen value lambda 2 equals to 5. For this we will have lambda 2 I minus A multiplied with C2 equals to 0. Again put the values 5, 0, 0, 5. We have multiplied it. Then minus A is 3, 4, 2, 1. And this whole has to be multiplied with C2, which is having the elements C12 and C22 equals to 0. Multiply this, we will get 5 minus 3, it is 2, 0 minus 4 minus 4, 0 minus 2 minus 2, and 5 minus 1 is 4. So just multiply this, we will have 2 C12 minus 4 C22 equals to 0, and minus 2 C12 plus 4 C22 equals to 0. We have two equations, two unknown variables, so we can easily find out the values. So C12 will come out to be 2 and C22 is equals to 1. So we have got our second eigenvector 2 and 1. So for we have got C1 and C2, so our complete eigenvectors we have known. C1 was 1 and minus 1, and C2 is 2 and 1. So we know that the modal matrix M, which we have to find out, this modal matrix, it is formed by the eigenvectors as its column. So it will also be a 2 by 2 matrix, C11, C12, C21 and C22. Put the values 1, minus 1, 2 and 1. So this is our modal matrix M. Now if we multiply our original vector A, which is a non-diagonal matrix, by this modal matrix, then it will be converted into a diagonal matrix. So we have to find out, we know that when we are multiplying, we are taking the new state vector x equals to mz, and our new state model was z dot equals to m inverse a m z plus m inverse b u, and y equals to c m z plus d u. So for this we have to find out the m inverse of the modal matrix, then m also we have find out. So let us find out this inverse, m inverse. Now inverse is calculated by dividing the adjoint of the matrix M by its determinant. So inverse is find out by dividing the adjoint of the matrix by the determinant. Now adjoint, how we can calculate? We have the modal matrix M as 1, minus 1 and 2 and 1. So we are going to change it, and the signs are also going to change. For adjoint we have and the determinant of matrix is 1 into 1 and minus into minus 2. 1 minus minus 2. So it is 1 plus 2, or we can say 3. So this is 3. So M inverse is 1 by 3, 1, 1, minus 2 and 1. This is our inverse, which we have calculated as inverse of matrix M. Now we are going to calculate this M inverse AM, CM and M inverse B. Okay, so we have M inverse is A matrix is 3, 4, 2, 1 and M matrix was 1, minus 1, 2 and 1. So we are going to multiply all these matrices and then we are going to calculate M inverse A M. Just divide this 1 by 3, multiply this inside. So we have minus 2 by 3. This is 1 by 3 and this is also 1 by 3. Then multiply this 3 into minus 1, then 3 into 1 and 4 into minus 1. Then 3 into 2, 3 2s are 6 plus 4 into 1, 4. Then we have 2 into 1, 2 and 1 into minus 1 is minus 1. Then we have 2 into 2, 4 and 1 into 1 is 1. So we are getting here 1 by 3 minus 2 by 3, 1 by 3 and 1 by 3. Then we have minus 3 plus 4. So 4 minus 3 is 1, 6 plus 4 it is 10, 2 minus 1 is 1 and 4 plus 1 is 5. Now we are going to again multiply these two matrices and then we will get the last as M inverse AM, which is minus 1 by 3 minus 2 by 3 minus 2 by 3 plus . So after diagonalization, the new state model will become So this is the new state model. So for this we have to find out M inverse AM, then M inverse B and CM. So first we will calculate M inverse and then we are going to calculate M inverse AM. So for calculating M inverse, we have to divide the adjoint of the matrix M by the determinant of M. Now how to calculate the adjoint? Adjoint is the transpose of the cofactors. So first we will find out the cofactors of matrix M. M matrix we have calculated, it is 1, 2, minus 1 and 1. Now cofactors of M will be, we have to, these two elements will be as it is and these two elements will be interchanged and their signs are also changed. So 1, 2 will come this side and it is, because it is positive 2 plus 2, so it will become minus 2. This minus 1 will become 1 and this 1 will be as it is. So these are the cofactors. Now adjoint will be transpose of this. So M inverse will become 1, minus 2, 1 and 1. Now determinant of the matrix M, we have to multiply this 1 minus minus 2, so it is 3. So we have written here 3. So M inverse is 1 by 3, 1 minus 2, 1 and 1. Now we are going to calculate M inverse AM. First we will write M inverse, which is 1 by 3, 1 minus 2, 1 and 1. Then we are going to write the A matrix, which is 3, 4, 2 and 1. Then we are going to write the M matrix, which is 1, 2, minus 1 and 1. we have written all the matrices, we have to just multiply them. So first we are going to multiply this 1 by 3 inside. One by 3 into 1 is 1 by 3. First we are going to multiply these two matrices. So we will get 1 by 3 into 3 and minus 2 by 3 into 2. Then 1 by 3 into 4 minus 2 by 3 into 1. Then 1 by 3 into 4 minus 1 by 3 into 1. 1 by 3 into 3 and here 2. This is 1 by 3 into 4 minus 1 by 3 into 1. And rest matrix is the same. 1, 2, minus 1, 1. Now let's multiply all these. We will have this is 1 by 3 into 3, so they are cancelled. Minus 2 by 3 into 2, so it is minus 4 by 3. So 1 minus 4 by 3, it will be minus 1 by 3. Then we have 1 by 3 into 4, so it is 4 by 3 minus 2 by 3. So it is 2 by 3. Then we have 1 by 3 into 3, that is 1 minus 2 by 3. So it is 5 by 3. Then 4 by 3 minus 1 by 3. It is again 5 by 3. Multiply this with 1, 2, minus 1 and 1. So let's multiply this. Minus 1 by 3 into 1 and 2 by 3 into minus 1. Then minus 1 by 3 into 2 plus 2 by 3 into 1. 5 by 3 into 1 minus 5 by 3. 5 by 3 into 2 and plus 5 by 3. So we are getting M inverse AM as minus 1, 0, 0 and 5. So you can see that when we are multiplying the A matrix, which is a non-diagonal matrix, when we are getting this M inverse AM, multiplying it with the modal matrix, then we have converted this into a diagonal matrix. All the other elements are 0, only the diagonal elements are present, and these diagonal elements are the eigen values. You can see that the eigen values which we obtained were minus 1 and 5. So diagonal elements are only the eigen values of the matrix A. Now we have to calculate M inverse B. B matrix is given to us in the question. It is 0 and 1. So again we are going to multiply 1 by 3 into 0 and minus 2 by 3 into 1. So it is minus 2 by 3. 1 by 3 into 0 and 1 by 3 into 1. So it is 1 by 3. So M inverse B is minus 2 by 3 and 1 by 3. Then we will calculate CM. C matrix is also given to us in the question. It is 8 and 1, and M is our modal matrix which we have obtained, that is 1, 2 and minus 1 and 1. Let's multiply this. 8 into 1 and 1 into minus 1. 8 into 2 plus 1 into 1. So we are getting 8 minus 1, that is 7, and 8 into 2 is 16 plus 1 is 17. So Cm is 7 and 17. So our new state model will become, we were having z dot equals to m inverse a m z plus m inverse b z u, and we have c equals to c m z plus d u. So just substitute the values. M inverse AM we have obtained, it is minus 1, 0, 0 and 5 diagonal matrix. M inverse B also we have calculated, it is 0 and 1. CM also we have calculated 7 and 17. And D is given to us in the question as 0. So this is our new state model, and you can see that in this new state model, this A matrix, which was earlier a non-diagonal matrix, it has been converted into a diagonal matrix, or we can say that we have obtained the diagonal form of the state model or the canonical form of state model. So in this video, we studied that how a non-diagonal matrix can be converted into a diagonal matrix and how it is used in the control systems. So I hope that this video is clear to you. Thank you.